Let's implement an algorithm to do matrix column vector multiplication via dot products. We start by looking back at our definition. That definition said that if we have a matrix A in Rm by n and a vector x in Rn by 1, we define matrix column vector multiplication given by A times x using dot products via an entry by entry approach. Specifically, the ith entry of the product b equals a times x is calculated as the dot product between the ith row of a and the vector x. In other words, b sub I, the ith entry of b, which is the entry in position I comma 1, row I, column 1 of the product a times x, that's going to be given as the dot product, the ith row of a transpose multiplied by x. If we look at what that means in terms of scalars, this is going to be the sum from k goes from 1 to n of a sub ik times xk. Here, the subscript value I on the entries of a aligns exactly with the output entry that I'm trying to find, b sub I. And then the summation index k aligns with the column index of entries of a and the row index of entries of k, and those are identical. We've seen previous videos on that topic. If you want to review, I'll go ahead and link that in the top right-hand corner of this YouTube video. Remember, step 1 of our program development process is to really understand the problem. I find that in all great coding, that starts with pen and paper analysis. Let's do that here. We want to create an algorithm to calculate b equals a times x from the definition using dot products. Specifically, we knew that the ith entry of b, the entry in the ith row and first column of a times x, was going to be given as a dot product between row I of a, written as a column vector, and the column vector x that was input to our algorithm. Using MATLAB colon notation, that means we're going to take the dot product between the ith row of a and x, which when we write individually, we actually can write the scalar values for the ith row of a and those of x. And in MATLAB code, we could write that as the dot product between the ith row of a and x. I do want to spend a minute analyzing this dot product versus this one, because we're actually going to depart from formal mathematics and get into crafty computer science. In formal mathematics, we define dot product operations in very, very special ways. Specifically say the dot product between two column vectors is a binary operation. In other words, it's an operation with two separate inputs. One on the left-hand side, which is an m by 1 vector, and then one on the right-hand side, which is an m by 1 vector. So that little dot, I'll have a vector on the left, vector on the right, both of which have m rows and 1 columns, and they're identical dimensions. And then the dot product maps to a real number. So the output is a scalar. The left operand and the right operand are column vectors with identical dimensions. That's the definition of the dot product between two column vectors that we do in a math class. We can also do a dot product between two row vectors, which is almost identical, still a binary operation, two input vectors. We have the left operand and the right operand. In this case, we say that the inputs are identically dimensioned row vectors. So the left input is a row vector with n columns, the right input is a row vector with identically n columns, and then the output is a scalar. If you remember back to our work with the d dot function, though, that we can take a little bit of a cavalier approach from the standpoint of formal mathematics. Specifically, we can define routines in MATLAB that allow us to deal with left and right inputs that do not have identical sizes. Remember that the dot product is an operation that takes two inputs. So we've got the left operand, the one that shows up to the left of the dot, and the right operand, or the right argument, the one that shows up to the right of the dot. And there's kind of different options. The left operand could be a column vector or a row vector. The right operand can be a column vector and a row vector. For many good reasons, nerdy mathematicians require that the formal definition be well specified, and that tradition in linear algebra is that the left and right operand have to have identical dimensions. So we Rm by Rm, and then we map to a scalar. However, in computer science, it is often useful to develop generality in our approach. So specifically, a crafty CS approach is, let's not worry about checking whether or not they have identical dimensions. Let's instead worry about whether or not they have identical sizes, because formally speaking, if I have a column vector and a row vector, as long as I have the same number of sizes, I can multiply the first entry by the first entry, add that to the product of the second entry times the second entry, all the way down to the end, and I actually get the same output, even though I'm breaking the rules of formalized mathematics. The same thing is true when I have a row vector and a column vector. I can code up a dot product algorithm that allows me to just multiply first entry by first entry, second entry by second entry, all the way down to the bottom to produce this with no problem because the outputs are identical. The reason this is useful is mathematics is not the same thing as computer science. In computer science, we have to think about memory structures, memory access, and using a bunch of computer science ideas that are outside the bounds of mathematics. Thus, it's useful to develop general functionality to take that burden off of the users and allow us some extra techniques. Of course, the last definition also holds. If we have the formal math definition with a row vector, dot product, a row vector, we can still calculate the output. The point of the matter, though, is that our dot product function, in other words, when we say b sub I equals the dot between ai and x, this is a computer science implementation that allows us to take the dot product between row vectors and column vectors in either order. That's exactly what we saw when we implemented our d-dot function from previous videos and also exercises that we did together. With all that in mind, let's strengthen our intuition about the connection between summation in mathematics and for loops in programming structures. Remember that for loops are designed to do the same operation a predetermined number of times, and that's exactly what we see here. We're doing scalar-scalar multiplication and scalar-scalar addition a predetermined number of times. We're thinking to ourselves for loops. Every time we run a for loop, we're going to use the same structure. First, we're going to initialize, and then we're going to run the loop. We already know that for each individual scalar, the scalar output is going to be the dot product between the ith row of A and the column vector X. And we might ask ourselves, well, what's the initialization? Of course, we can always add 0 to any output and do nothing to it. So let's go ahead and generalize and say we're going to initialize each individual entry of some vector y to be 0, and then we'll just add that to the dot product between ai and x, and that will give us the ith entry of the output that we desire. Just like we've spoken about in previous videos, though, that this would require a bunch of different memory structures. It would require a vector y, which is our initial vector, A, the vector x, and then a new output vector b. One of the things in computer science is that we want to be very crafty about how we use memories. Instead of having to create a new output vector, let's just reuse the initial vector since this was used as a starting point and overwrite those starting values with the output that we desire. With those ideas in mind, we now have a guess at our algorithm. We're going to initialize y to be the 0 vector. Then we're going to drop into the for loop, moving down the individual rows of y, and we'll say that the ith entry of y is going to be the initial value plus the dot product between the ith row of A and the vector x. Here we're using the CS approach that says as long as the two input vectors have the same number of entries, we can find the dot product between those. We're now ready to actually start coding up our first guesses at an algorithm here. So we're going to initialize our vector y to be zeros. It will be a column vector. And then we're going to run the loop that says that the ith entry of y is going to be the previous entry in that location plus the dot product between the ith row of A and the vector x. In a previous video, we've already started our sandbox for BLAS Level 2 explorations. Remember, BLAS stands for Basic Linear Algebra Subprograms. So here we did the matrix column vector multiplication via linear combinations, and we played with that. Let's go ahead and just duplicate that file. And what we'll say is that this is not matrix column vector multiplication via linear combinations. This is matrix column vector multiplication via dot products. So we'll go ahead and just copy that driver. Let's open it up and start editing. This is one of the most beautiful things about writing code that works in the first place. We can reuse it in the future. So we'll go ahead and change the order of this. We're not ready for the matrix column vector multiplication double loop yet. We'll do that in a second. So here, let's uncode the first level of loops. There we go. We have our test data that we've already used. We are going to generate the output of this that MATLAB generates. And then, you know what? We can actually go ahead and comment this and then run. Change folder, of course. And then what we'll do here is take a look at ymat to remind ourselves what the output we desire is. Let's uncomment this again. So we go here. We know that this is going to be getting the dimensions of matrix A. And then this is going to be matrix column vector multiplication algorithm using dot product operation. Now, of course, we've just said initialize the vector y to be all zeros. In this case, we're going to go over the rows of our vector y. And then we're going to say that the ith entry, the entry in row I, comma 1, by the definition up here, is going to be the previous ith entry plus the dot product between the two. Here, for you viewers at home, you could actually use your dot product algorithm that you coded up as part of the work in BLAS Level 1 routines. I'm going to use MATLABs in this moment because, truth be told, I haven't coded up my own ddot function. I've been too busy putting together these videos for you. Once I have that, I could actually run the darn thing. And when I do that, I can compare ymat, which is MATLAB's output, to my output, and I notice they're identical. Let's go ahead and capture that code, and we'll talk about verify our output. So we'll put that there, and that gives us a way to just check that it works the same every single time. Y'all know my style as your coach and mentor. I love to encourage you to not only develop an idea of what the code is doing, but actually to visualize what's happening as you progress through each loop. Here, we're going to use that same visualization structure. Over on the right-hand side, we see our math operation, which is going to be to add a vector y to the matrix column vector product A times x. We map over to the pseudocode version, which is to take the ith entry of y as the previous initialized value plus the dot product between the ith row and the vector x. Let's do a visual progression through each of the individual steps. When we start, we have three separate vectors in memory. We have the vector y, we have the matrix A, and we have the vector x. Y has been initialized to be whatever values we want. In our case, we thought about those as 0. Strictly speaking, they could be non-zero, right? Once we drop into the first iteration of our for loop where I is equal to 1, this is going to allow us to calculate the first value that we want. To do so, we access the first row of A and dot it with the vector x. So we move across the rows of A down the vector x, we add that to the previous value, and that updates entry 1 of our vector. When we go into the second iteration of our for loop, we move down to the second row of A, move across the columns, and then down the rows of x. When we add that to the previous value of y, we get the second entry of our output. Let's move down to the third iteration. In this case, we process the third row of A and dot it with the vector x to get the third entry of the vector y, and we do that one more time where we update the fourth entry of y with the dot product between the fourth column of A and the vector x. Once we have this, we end our loop and we return the value of y, which now stores the updated version. Notice in this case, we progress through the columns of A, down the rows of x. Depending on how our language stores and accesses matrices, the difference between column partitions and row partitions actually means a lot when we're trying to optimize code. Now that we know that our BLAS Level 2 operation is working, where we use BLAS Level 1 to feed into BLAS Level 2, we might actually want to go down to the entry by entry version and not process the entire rows of A in one shot, but actually move across the individual entries in each row. Let's go ahead and comment this. And we'll go down here. We're going to do a matrix column vector multiplication via dot products. Let's uncomment the entire chunk. And I think I made a little mistake here. This should be commented. Here, we'll delete that old code and replace it with a new code. And we'll go ahead and uncomment that code that we've been working on. So what we're going to do here, this actually accesses the entire row at once, but that relies on BLAS Level 1. Let's actually go down into that loop and see what's happening. So as we move across the row, we're going to go from K goes from 1 to N, since this has N entries in it, and then we'll go ahead and end. So let's replace the dot product with what the dot product is actually doing. So in each dot product, I'm going to move across the rows of A, where I multiply the entry in each column by the corresponding entry in the same row of the vector x. So this would be x k comma 1. In other words, what we've done is we replaced the dot product with the actual representation of what we're doing in that dot product. When I run this, notice that I actually get the same output. In other words, we can refine our algorithm to go down into entry by entry access of the matrix A, and that's exactly what we've done in this case. Let's visualize what's going on here. We use that same visualization structure. The math operation that we're doing is y plus A times x. We now go over to the pseudocode, which is a nested for loop. One of the for loops moves down the rows, the other one across the columns. Here we start with rows on the outside and move across columns on the inside. The inner update is going to be replace the new value of y with the old value of y plus the product of aik times xk, which is exactly what we've just seen. When we initialize this for loop, we set the vector y in memory, also the matrix A and the vector x. Once we've done that, we drop into the first part of the outer loop. So let's say that I is 1 and k is 1. I is going to go through the individual rows. So I'm going to start with row 1, column 1, and I update the first entry with the previous value times A11 x1. Then I go to the next entry, which is k equals 2. So I'm going to move across the rows. Now I take A12 x2 and I add it to the previous value. And I go all the way to the last column of my first row, which is A13. I multiply that by x3 and I add that to the previous result. Notice that in A, we access the first row and then move across the columns in that row, whereas in X, we move down the rows of that vector. Once we finish that, we update the outer loop index. I goes to 2. We go to the second row, first column. We add the product of that entry times x1 to the previous value. We move to the next column, which is A22 times x2. We add it to the previous value. We go again, A23 x3, and we continue in this way. Now we're going to update to the third row. We move across that row, each time individually updating the previous value. Then we move to the fourth row, which is the last one. Here we take the first entry in the fourth row multiplied by x1, second entry multiplied by x2, third entry multiplied by x3. And at this point, we exit the loops and our output vector y has been overwritten with the exact value that we wanted. With that, we see we have a working algorithm to implement matrix vector multiplication via dot products, both at the BLAS level 2 and BLAS level 1. One of the major inspirations in linear algebra is actually to optimize these and create extremely fast algorithms. We're not going to touch that in this case, but you all are setting a foundation to be able to think about exactly how to optimize those. That leads us to the community challenge of this video. Go ahead and write the similar script for the row vector matrix multiplication and create the visuals for yourself, always thinking, how is the algorithm that I'm working with related to the way that I process my input data? Am I moving across the rows? Am I moving down the columns? How does that whole process work? Can I visualize it? I look forward to seeing your responses in the comments to this video, as well as questions, concerns, feedback. I love getting that. Thank you so much for your attention, and the next video will actually do exactly that. I'll see you there.